Have you ever, actually stopped to think about what happens when you load a web page? Or, stream a video like you're probably doing right now?
Most people definitely don't. It just magically works.
Right. We just think of the internet as this continuous invisible pipe that opens up and pours data into our homes. But right now, your device is quietly making, thousands of invisible split-second negotiations with complete strangers across the globe.
Yeah, it's a nonstop frenzy. Just microscopic handshakes and routing decisions happening right under the glass of your screen.
It's wild. So today we're doing a deep dive into some system administration notes, specifically Class 11, which covers packets and protocols. And the mission here is to really lift the hood on the internet. We want to look at those specific invisible rules that, basically keep the digital world from just collapsing into total chaos.
Because it really is a delicate balancing act. The concepts from this syllabus, they're the absolute foundation of how every single modern network functions.
Exactly. So let's start with what you're saying about the pipe. The fundamental illusion of the internet is this idea of a continuous stream of data. Because when you download a massive file, it isn't actually moving as one long, unbroken flow, right?
No, not at all. You can't just, open a valve and let data flow indefinitely. All information traveling over a network gets chopped up into these small, discrete pieces called packets.
Okay, so it feels like trying to mail a massive 1,000-page novel to a friend. But the Postal Service is like, hey, you are only allowed to write on postcards.
Yeah, that's actually a great way to picture it.
So you have to write a few paragraphs on postcard number 1, drop in the mailbox, write postcard number 2, and so on. But why limit the size? Wouldn't it be, vastly more efficient to just send the massive file all at once instead of managing millions of tiny postcards?
Well, it seems like it would be, but the technical limitations really come down to physical realities on the network. First off, you've got local network sharing. Limiting the packet size prevents one single device from completely monopolizing the local segment.
Oh, I see.
Yeah, if you could send a terabyte file as a single uninterrupted transmission, literally no one else on your local Wi-Fi would be able to send a basic email or load a web page.
Right, because the network would just be totally blocked until your file finished.
Exactly. It's basically a forced courtesy.
Like a talking stick in a group meeting.
Uh-huh.
You get your turn, you send your small packet, and then you just have to yield the floor for a microsecond so someone else's stuff can slip through.
Right. And beyond the courtesy aspect, there are just hard physical constraints. The network interface cards, so the physical chips inside your computer that handle the connection, they have strict limits on how much memory they can buffer at any given millisecond.
Ah, so they literally can't catch the whole file at once.
Right. Standard Ethernet packets are usually capped at a payload of around 1,500 bytes. Your computer's hardware just isn't designed to catch a single, giant, millions of bytes long electrical signal. It needs those bite-sized chunks to process everything efficiently.
Okay, so we've got our novel chopped up into thousands of postcards, but those postcards don't all travel together in a neat little organized line, do they?
Oh no, the journey is totally chaotic, entirely unpredictable.
Yeah.
The route a packet takes from the source to the destination, it doesn't have to be the same for every packet in the sequence.
So postcard 1 might hit a router in Chicago and get passed along totally fine.
Yeah, and then by the time postcard 2 reaches Chicago, that exact same router might be bogged down with heavy traffic, so the system just dynamically routes postcard 2 down through Atlanta instead.
Wait, really? So the physical path is being recalculated in real time for every single fragment of the file.
Yep, exactly.
That means packets can take completely different paths across the globe, which implies they can arrive out of order, right? Like postcard 50 could easily show up before postcard 10.
Oh, it happens all the time. And with all those hops between different routers, some packets just get dropped or lost entirely.
Just gone into the void.
Yeah, routers get overwhelmed and just drop data. And remember, at the lowest level, these packets are just raw streams of electrical zeros and ones. The only reason they survive this crazy journey is because of metadata.
Right, the headers.
Exactly. Structured information attached to the packet telling the network what to do. Every packet has a header, which is basically the address block written on your postcard.
Okay, so looking at the notes, I see two main types of addresses constantly referenced in these headers: ME addresses and IP addresses. If they're both just pointing to a device, how do they actually differ in practice?
Good question. So ME address, media access control, is a physical hardware address. It's permanently burned into your device's network chip. And it's used exclusively for moving data locally, like on your immediate network segment.
So the MEAC address is what gets the packet from my laptop just to my home Wi-Fi router.
Exactly, but an IP address internet protocol is what routers use to figure out how to pass the packet along to completely different networks halfway across the world.
Okay, I think I get it. So the IP address is the final destination, like the specific street address in London written on the postcard. But the MV address is just like the local mail carrier physically handing it off to the neighborhood post office.
Oh, that's spot on, yes. And even when a packet is destined for a server in London, your laptop still routes it locally using the MC address of your gateway router.
Oh, interesting.
Yeah, so the router receives it via the MC address, strips that local header off, looks at the IP address, and then decides which outgoing cable to push it down next.
So if we have millions of packets flying around, taking different routes, dynamic handoffs, getting lost, how do we even know if the final destination is online? Like, if I'm sending data into the void, I'd want to test the waters first. Is there a way to just, tap the microphone and see if anyone's listening?
Yeah, there is. And this brings us to a really fundamental management protocol called ICMP, the Internet Control Message Protocol.
Okay.
So ICMP isn't used for sending your novel. It's used for sending control messages just to check and manage the network itself.
Like the ping command.
Exactly. Ping is the most common use of ICMP. It's a quick, lightweight way to verify if a route actually exists to an IP address and if the device on the other end is online and willing to talk.
So it's basically basic sonar. Are you there? Yes, I am here.
Right. You send an ICMP echo request and you get an ICMP echo reply back.
But that brings up a much bigger operational problem, I think. If the network is dropping packets because a router in Chicago got congested, how do I know a sensitive transaction actually went through?
What do you mean?
Well, if I transfer $1,000 to my bank and the specific packet containing the zeros gets lost in transit, I don't want the bank server thinking I only transferred $1. Basic IP routing doesn't seem to care if the packet gets there.
You're totally right. Basic routing is entirely what we call best effort. It doesn't care. So to fix that reliability problem, we rely on a higher level protocol to enforce order on top of the chaos. And this is TCP, the Transmission Control Protocol. It operates at the transport layer, layer 4, and it is connection-oriented. It absolutely guarantees delivery, and it guarantees that the info will be reassembled in the exact sequence it was sent.
Okay, but how does it pull that off mechanically if the underlying network is still, dropping the mail? How does TCP guarantee the novel arrives perfectly?
It manages this through a really clever mechanism called a sliding window. When your computer sends data using TCP, it meticulously numbers every single packet in the header, sequence 1, 2, 3, 4.
Right.
As the receiving server gets them, it's required to reply back with an ACK and acknowledgement. It essentially says, hey, I have received up to packet 4. I am now expecting packet 5.
So it isn't just sending blindly, but waiting for an acknowledgement for every single packet would be agonizingly slow. Like send 1, wait. Send 2, wait.
And that is exactly where the window comes in. The sender doesn't wait for an ACK for packet 1 before sending packet 2. The two computers negotiate a window size, let's say 100 packets.
Okay.
So the sender blasts out packets 1 through 100. As the ACKs start rolling in for those early packets, the window slides forward, allowing the sender to transmit 101, 102, and so on.
Oh, that's smart. But what happens when the ACK just never comes? Let's say packet 50 gets dropped by that overloaded router in Chicago.
Well, the sender actually maintains a timer for every unacknowledged packet. So if the timer for packet 50 expires and no ACK has come back, the sender just assumes it was destroyed and automatically retransmits packet 50.
Wow. What if it wasn't destroyed, though? What if it was just delayed?
Yeah, that happens.
Okay.
If the receiving server gets duplicate packets like the original delayed packet 50 shows up and then the retransmission arrives right after it, the TCP software on the receiving end sees the duplicate sequence number and just silently discards the extra copy.
Man, it is an incredibly rigorous accounting system. I can totally see why web browsing and bank transfers rely on TCP. But before any of this data counting even happens, TCP has to formally establish the connection rate. It uses a three-way handshake to set the ground rules. Can you walk through how that negotiation actually works?
Yeah, absolutely. Because TCP requires a reliable two-way connection, it has to make sure both sides are ready. So step 1, the source device sends a packet with the SYN flag set. SYN stands for synchronize.
Okay.
It includes the initial sequence number it plans to use. It's basically stating, I would like to open a reliable connection with you.
So step 1 is SYN. Hello, I want to establish a connection. Then the server gets it. What's next?
Step 2. The destination server responds with a packet that has both the SYN and ACK flags set. So SYN ACK. This tells the source, I acknowledge your request to connect, and I am sending you my own synchronized request to establish my side of the street.
Got it. Step 2 is SYN ACK. I acknowledge your hello, and I am saying hello back.
Exactly. And finally, step 3. The source sends a final ACK packet acknowledging the server's SYN, and only after that three-way handshake is completed does the actual data like the HTTP request or your bank transfer start flowing.
You know, this handshake is incredibly polite. It requires both sides to allocate resources and agree to communicate. But just looking at the mechanics of this, it seems highly vulnerable to bad faith actors.
Oh, big time.
Like, it relies on everyone following the social contract. What if, I don't know, a malicious script initiates thousands of handshakes, sending a flood of those first SYN packets, but then the attacker just walks away and refuses to send the final ACK?
Yeah, you've identified a classic vulnerability there. In fact, the basic architecture of IP routing has literally been described by security analysts as an attacker's paradise. What you just hypothesized is called a SYN flood. It's a specific type of denial of service, or DOS attack.
So how does walking away from a handshake actually take a whole server down?
Well, think about what the server has to do when it gets that initial SYN packet. It sends the SYN ACK, sure, but it also has to prepare for the incoming connection. It allocates a small chunk of its own memory to track the sequence numbers and keep the port open, just waiting for the final ACK.
Oh, I see.
These are called half-open connections. So if an attacker sends a massive continuous stream of spoofed SYN packets, the server dutifully allocates memory for every single one of them.
Because it's too polite?
Exactly. And eventually, the server's memory pool for new connections just fills up entirely. It becomes completely frozen, waiting for thousands of ghost connections to finish handshaking.
And when a legitimate user tries to connect,
the server has no resources left to respond. It's effectively offline.
That is a devastatingly simple way to break a system. It really forces you to wonder why the engineers who built this architecture designed a protocol that could be so easily manipulated. It was a massive oversight.
It does, but you have to view it through the historical context of how networks developed. The creators of these foundational protocols, they weren't building for the public internet we have today.
Right, it wasn't public.
No, the original networks, like ARPANET, were privately controlled environments. They were connecting trusted academic and military research facilities. Public anonymous access wasn't even the paradigm.
So they just assumed everyone was friendly.
Exactly. The entire architecture started as an experiment just to see if disparate computer systems could route messages reliably at all. Weaponized trust, where someone intentionally manipulates a polite handshake just to consume memory, that was simply outside the threat model of a closed research network.
We basically took an architecture of inherent trust and scaled it to connect a planet full of strangers.
Yeah.
That definitely explains the vulnerabilities. But okay, moving past security, TCP has a ton of overhead. Handshakes, sequence numbers, timers, acknowledgements.
A lot of accounting, yeah.
Right. So if I'm streaming a live video feed, I don't want the stream to freeze for 3 seconds while the protocol retransmits one lost packet. Sometimes I don't care if the data is perfect, I just need it fast.
Exactly. And when speed is prioritized over perfect reliability, the network uses a totally different transport protocol, UDP, the User Datagram Protocol.
So how does UDP strip away all that TCP overhead?
It just removes the accounting entirely. UDP is a connectionless protocol. There is no three-way handshake. There are no sequence numbers tracking what arrived, and no ACKs.
Wait, really?
Yep. The source just fires the packets at the destination IP address as fast as the network interface can push them. It is purely fire and forget.
It's like throwing a handful of darts at a dartboard as fast as you can.
Yeah.
You don't stop to verify if one bounced off the wire, you just keep throwing.
Perfect analogy.
So if a packet arrives out of order, or gets dropped by a router, the receiving application just accepts the loss and moves on.
And that's actually perfectly acceptable for specific use cases. Like with live audio and video streaming, latency is the enemy. If you drop a UDP packet during a video call, a few pixels might glitch on your screen for a fraction of a second, and then the stream just continues.
But if that same call ran over TCP?
Oh, the protocol would realize a packet was missing, halt the entire video feed, request a retransmission, wait for the packet to travel across the country, insert it, and finally resume the video. You would experience constant, agonizing stuttering.
Yeah, glitchy real-time video is far better than perfect video delayed by 5 seconds. So the application basically dictates the transport layer. A web browser loading a page needs TCP because a missing line of HTML breaks the whole website. but a video call rides on UDP.
Yes. For example, HTTP, the protocol driving the web, relies on TCP to ensure the text and images load flawlessly. SSH and SMTP for email use TCP too. But another crucial system that runs over UDP is DHCP, the Dynamic Host Configuration Protocol.
Right, DHCP. That's the system that actually assigns an IP address to a device, isn't it? Like when I connect my laptop to a new Wi-Fi network, my laptop doesn't have an address yet. So it essentially shouts into the local network using UDP, saying, hey, I'm new here. Can somebody give me an IP address?
That's exactly it. It entirely removes the need for humans to manually type in network configs for every single device they connect.
But this brings up a glaring mathematical problem. We have billions of devices, phones, smart TVs, laptops, refrigerators. Every time one connects, DHCP hands it an IP address. But the original IPv4 address base only has about 4 billion unique public addresses. We ran out of public IPs a long time ago, didn't we?
I did.
So how are we continually connecting new devices if there aren't enough addresses to go around?
We survive through a very clever mechanism called NAT, network address translation. Because of that shortage, the internal devices on your home or corporate network do not get unique public IP addresses.
Oh, they don't?
No. DHCP hands them non-routable private IP addresses. These private addresses are meant only for local use and are completely invisible to the broader internet.
Okay, let's visualize this. I think NAT acts a lot like a receptionist at a large corporate office.
Okay, let's hear it.
So the company has one public street address. All mail from the outside world is delivered to that single public address. Inside the building, there are hundreds of employees with internal desk extensions. When an employee wants to send a letter, they hand it to the receptionist. The receptionist puts the main company address on the return envelope.
Right.
And when a reply comes back to the building, the receptionist looks at their ledger, remembers which specific employee asked for that info, and routes it internally to the correct desk.
That is exactly how it works. The mechanism of NAT works almost exactly like that ledger. When your laptop, which is sitting on a private IP like, say, 192.168.1.5, when it requests a web page, the packet hits your home router.
The receptionist.
Right. The router pauses the packet and rewrites the header. It strips out your laptop's private IP and replaces it with the router's single public-facing internet IP.
But if there are 5 laptops in the house all browsing the web simultaneously, how does the router know which incoming packet belongs to which laptop when the web server replies?
It uses port numbers. When the router translates the outbound packet, it also assigns a unique temporary source port number, say port 5000, and logs this in its internal NAT table. It basically says private IP 192.168.1.5 is using port 5000 for this connection.
Okay.
So the web server sees the request coming from the router's public IP on port 5000, and it sends the website data back to that exact IP and port.
Oh, and then the router catches the incoming data on port 5000, checks the ledger, sees that port 5000 maps back to the laptop at 1.5, rewrites the destination address, and passes it locally to the laptop.
Exactly.
So the laptop thinks it's talking directly to the web server, and the web server thinks it's talking directly to the router. Neither side knows the translation is happening.
It is entirely seamless. NAT basically allowed the internet to keep growing despite the hard limits of the original IPv4 design. But because all this happens automatically, the actual mechanics of the network remain totally hidden from the average user.
Which begs the question, how do we actually look at this invisible traffic?
Yeah.
If I want to see the 3-way handshakes, the raw packets, the sequence numbers flying across my network card, how do I peer into the matrix?
Well, system administrators use packet capture tools. The syllabus material we're reviewing focuses heavily on a command line tool called TCP dump.
Okay.
It allows you to capture and read the raw network traffic arriving at your network interface in real time.
You just run the command and your terminal floods with the raw data of the internet. You can use flags like -A to print the packet contents in ASCII, which actually lets you read the unencrypted plaintext payloads, like the raw HTML of a website, right there in the terminal. And you can also use --jar to write the raw capture data to a file and -shard to read it back later for analysis.
Yeah, understanding TCP dump is critical for troubleshooting. Which actually brings us to the practical application for you, the listener. If you are following along with this course material, Lab 11 requires you to use TCP dump and another tool called T-Shark to capture your own local network traffic.
Capturing your own traffic being the operative phrase there. The syllabus includes a massive warning about how you configure these tools. By default, a network card only processes packets destined for its specific MSE address. But packet capture tools can put the card into something called promiscuous mode.
Right, which forces the network card to read every single packet passing over the local network segment, even the ones belonging to other people.
And depending on the network you are on, capturing other people's traffic without authorization is essentially wiretapping.
Yeah, it's a huge deal.
It can lead to severe legal and disciplinary issues. So, for Lab 11, do not put your interface into promiscuous mode. When using TCP dump, you must use the -out flag, which explicitly disables promiscuous mode.
Absolutely. And to use T-Shark correctly without running into permissions errors, you need to ensure your user account is added to the Wireshark group. You can do this with the command usermod-a-g Wireshark administrator, and then just log out and log back in for the group policy to take effect. Stick to analyzing your own MSC and IP address traffic. Use the -w and -r flags to save your packet captures and analyze the handshakes we discussed today.
We've covered a lot of ground today. We've seen how the internet relies on fundamentally trusting protocols, like the TCP handshake, to maintain order amidst the chaos of routing. And we've seen how, as the internet scaled far beyond its original design, we had to patch over those inherent vulnerabilities and limitations with retroactive measures like NAT to hide our devices and conserve addresses.
Yeah, it really forces you to look at the internet not as a finished product, but as a continuously evolving series of compromises. The foundational layers assume a level of trust that simply doesn't exist anymore.
Which leaves you with a final, provocative thought to mull over. Considering the structural patches, the vulnerability to SYN floods, and the fact that basic routing has zero built-in security, what would the internet look like today if we could tear the entire thing down? If we could redesign the base layer from scratch, assuming from day one that the whole world is hostile, how would the fundamental protocols of communication change? Next time you load a web page, take a second to appreciate the chaotic, miraculous ballet of packets, timers, and overworked NAT routers that make it all possible. Thanks for diving deep with us.